Okay, so then finally, the last condition, when r approaches infinity. So both angular momentum and Coulomb's terms can be ignored because both forces become very weak when the electron is far from the nucleus. Okay? So the only thing that the electron has to consider is kinetic energy. Look, we got rid of all of these potential terms when the particle is very far away. And you can see here that this is a Schrödinger equation we've already solved, right? And you can see if I keep going through this on our standard ansatz method, right? So I add that over to the other side. That's going to be plus 2 mu e over h bar squared times u of r equals 0. We've solved this thing. This is literally just our one-dimensional particle in a box wave function, okay? And so now, as you're looking at this, you notice that there is this other condition here. This sign means assuming I can spell, it means asymptotically equal to. So there is an asymptote that this thing is approaching. And that asymptote is actually given by our boundary condition that E must be less than 0 for all bound states. And I've already showed you what that asymptote looks like. Here it is, right? As the electron is getting very, very far to the nucleus, or excuse me, very far away from the nucleus, look, these two potential energy terms, they don't quite get to 0, but you can see that they're approaching 0. So when the electron is very far away from the electron, we're kind of in this region right here where we're approaching this asymptotic limit of E being 0. Okay? So we need E to be less than 0 for all bound states. And so what that means is when you're looking at this and you're going to set up the solution, okay, you're going to get something like K squared equals negative 2 mu E over h bar squared. And at first inspection, you might say, well, that's going to have imaginary solutions, but it's not. It's going to have real solutions because E already is negative. And so because that has a real solution, look, our term just becomes this simple E to the negative root of R, okay? And the reason why we just have the negative term and not the positive root is because of that asymptotic limit, okay? So I've been talking for 38 minutes, so it's time to cut it off. So this is where I'm going to end this. So we're going to put all of these approximate solutions together. So we've come up with 3 approximate solutions. 1, when the electron is very far away. 2, when the electron is very close, but it has angular momentum. 3, when the electron is very close, but it has no angular momentum. Okay? So when we put all 3 of those solutions together, we get something that looks like this. So we get this, and we're going to remember we've got U of R equals R times, let's see, what did I say? Oops. It's supposed to be R times R of R. So, and we're not gonna actually solve this thing ourselves. I'm kind of showing you the approximate way to solve this, okay? So when we go to get back to our radial wave function, R, we have this R raised to the L power, dominant when the electron is close to the nucleus. We have this decaying exponential in R, dominant when the electron is far from the nucleus. So that was the solution I just showed you. And then now we get this polynomial in R. That was our solution for when there's no angular momentum. And that bridges this kind of in-between region where there is angular momentum and potential energy that both affect the electron's position. Okay? And so some very smart folks have solved this problem and normalized it. And we're not going to do it ourselves, but I'm just going to present to you now the solution. Okay, so collecting our constants, we know that A naught is the collection of all of these constants. For convenience, this term rho is used to collect the 2zr over n A naught, where n has its usual meaning, that's quantum number n. Okay. And so now what we get, so you can see this r raised to the L power, that becomes rho raised to the L power, because that approximate solution of r raised to the L power didn't contain all of those constants. Okay, and right, the Bohr radius is in that package. So there's a ton of constants here that are actually being raised to the L power. Okay, so this is that term right here. So this crazy thing, this L to the 2L plus 1 to the sub n plus 1 of rho, this is called the Laguerre polynomials. So this is the bridge that connects the solutions when r is very close or when the r is very far away. It also provides the connection for n and L. And I know that the notation of this looks fearsome, but it's really not. And when the Laguerre polynomials were developed, like I said, they actually provided the connection for n and L. And that connection becomes L takes on all values 0, 1, all the way to n minus 1. So these polynomials have standard notation based on that. Okay. So for example, when n is equal to 1, we know that L can only equal 0. And if I were to go and look up that Laguerre polynomial, then the notation of that polynomial would be, it would be written as L1n2, right? Because when L is 0, 2 times 0 plus 1 is 1, and when n is 1, L is 2. Or excuse me, that bottom term is 2, okay? So so in this notation, when we say L12, we know that we're dealing with n equals 1, L equals 0, okay? And then finally, we have this decaying exponential in r given to us by this term here. Okay, so that's about 42 minutes. That's kind of a long lecture. Apologies for that. So we're going to pick up right where we left off here. Okay, folks.